please.
Okay. Yeah. Thank you. Thank you all. All right. So this is going to be a little bit of a different talk than what you've heard this morning. It was supposed to be sort of a keynote, so I thought I'd give a slightly higher level talk. Hopefully, it'll be clear. Everything will be clear to everyone, and enjoyable. So let's get started. What I wanted to talk about a little bit is basically how to use lattices for folding techniques. Okay, so we'll see how this works, and this is all joint work with Boneh Chen. There are 2 papers on this now, and actually there's a third one that I will talk about later. Boneh, by the way, is out looking for a position, so if anybody's interested in hiring him, he's fantastic, and you should do it. All right, so with that, let's get started. So let's see. So what are we talking about? So the first thing I have to do is just well, everybody here knows what a SNARK is, but I do have to set terminology. So let me just remind you that a SNARK basically operates on a circuit. So it's a circuit, it's an arithmetic circuit over some finite field. It takes a statement and a witness. I'll typically be using pre-processing SNARKs. So there's a setup algorithm that will pre-process the circuit to generate the proving key and the verification key specific to the circuit. And then these are given to the prover and the verifier. And as usual, the prover is given X and the witness. The verifier is given X and the proof and decides whether the proof to believe the proof is not. Yeah, so everybody here should be familiar with this. I hope that's not new. If this is new to someone, then you're probably in the wrong room. Okay, so as usual, we want the proofs to be succinct and they need to be fast to verify. We allow the verifier to run in linear time in the size of the statement because the verifier has to at least read the statement. This is, by the way, kind of the reason why we need a verification key. The verifier doesn't have enough time to even read the circuit. Yeah, and so if it can't read the circuit, it has to have someone summarize the circuit for it, and that's the purpose of the setup algorithm. It generates a verification key that's a summary of the circuit, which is then allows the verifier to check the proof, even though the verifier can't read the circuit by itself. Okay, good. So I thought I'd start off with a few examples of things that we do with SNARKs that have nothing to do with blockchains. They're just kind of interesting examples, and then we'll move on to LatticeFold. One thing I want to point out is kind of these examples of applications for SNARKs are only possible because SNARKs have developed so rapidly in the last couple of years, and a lot of that is only possible because of their blockchain applications. So what I want to show here is applications of SNARKs that have nothing to do with blockchains, but those applications are only possible because of the effort that the blockchain community has put into developing good SNARKs. I think we don't say this enough, that really it's kind of, first of all, congratulations to all of us, to all this community in developing in this amazing progress in making things like this possible. But a lot of this is also possible because there is such a strong business need for these things to develop. But let me start with the examples. So the first example we call ZK-Pi. This is joint work with my students, Evan Laufer and Alex Ozdemir. And the question is basically, how can we prove knowledge of a lean proof? Yeah, so specifically, in this case, the statement that we want to prove is that I have a lean proof. Lean, as you know, is a language well, it's a theorem proving language. You can state theorems in lean, and you can state proofs in lean. So X, the instance, is going to be a theorem in lean. The witness is going to be a proof of the theorem in lean, and the circuit that we're going to be using is a circuit that basically checks whether W is a valid lean proof of the statement X. So really what the circuit has to do is just implement effectively the lean verifier. So this work was basically, how do we build a ZK SNARK system that can encode the lean verifier? So that's exactly what ZK-Pi does. The cool thing about this is that no matter how long your lean proof is, the SNARK proof is going to be really short. Yeah, so it's like under a kilobyte. Again, no matter how complicated the proof is. So that's kind of the point. I like to say that Fermat would have loved this. He didn't have enough space in his margin to write his proofs. So what he could have done is he could have used ZK-Pi to take his proofs, compress them to a short proof, and then write those proofs in the margin. I gave this talk to a math audience at some point, and they said, this is not possible. You can't take a long proof and compress it into a short proof. And they're right, because really what this thing actually proves, what this compressed proof actually proves is one of 3 things. Either the theorem is correct, or somehow you maybe, let's say, broke SHA-256, right? So it's not really proving the statement. It could be that the crypto is wrong, or you got really, really lucky. Yeah, it's like one of those three things must happen, and that's basically what these proofs do. I have to say, like one of the interesting things about this is, yeah, so Fermat could have used it, but let's be a bit more philosophical for just 1 second. It's actually very likely. So here's a bold prediction. Yeah, it's quite likely that in this century we'll have a proof of the Riemann hypothesis, but that proof will be generated by an LLM. Yeah, the proof will actually, well, not an LLM, it'll be generated by a machine learning model. Yeah, the proof will be written in Lean, so we're guaranteed that it's correct, but it might end up being like 1 billion pages. Yeah, so no human will ever understand the proof, even though we know it's correct, and we'll never even be able to print it out on any piece of paper. The nice thing about that is we can take that proof, stick it into ZK Pi, generate a short proof that the Riemann hypothesis is correct, and at least we can print it on our shirts and say that we have a proof on our shirt that the Riemann hypothesis is correct. Or SHA-256 is broken, or we got really lucky. One of those. What's interesting about ZK Pi is, so as you can see here, it can generate, so Lean, I should back up just a second. Lean has a standard library with standard axioms like the pigeonhole principle and all sorts of theorems that go into the standard library. It also has MATLib. MATLib, by the way, is a really impressive project. So MATLib is a project that tries to encode most of undergraduate math in Lean. Yeah, so it's lots of, what can I say? It's a formalization of lots of mathematics along with formal proofs of basic theorems in these areas. So because these, so let's see. So ZK Pi actually doesn't implement all of Lean 4. It implements a subset of Lean 4. As a result of this, we can actually prove, not all of these standard libraries, but a fair fraction of these of the theorems in these libraries. There's actually a lot more work to do here if anybody's interested in completing the verifier and building like a full verifier for Lean 4. Hopefully, we can kind of get all the theorems proved in SNARKs from these systems. So there's actually a bit more work to do here. Okay, good. Right. So that's one example that I wanted to give for how to compress proofs, how to compress Lean proofs. The second example I wanted to give is more in the machine learning setup, which is what we call X-proof. So X-proof works as follows. So the goal is basically what we're starting to see in the real world. So we have, like, let's say, a bank that trains a model. This model is supposed to decide whether your mortgage application should be accepted or rejected. Yeah, so you send your financial data over, so you send your financial data over to the model. The model evaluates your financial data and then sends you a response saying, your loan application was accepted or rejected. One problem here, by the way, so when you get your response, you might be wondering, well, why did the model decide to accept my application or reject it? It turns out there's actually at least in the US, there's a regulatory requirement to provide an explanation. You can't just say yes or no. You have to say you were rejected because of this and that reason. So how do we do this in the context of machine learning? Well, maybe some of you know there's this algorithm. It's a fairly famous algorithm called LIME. Might be good for you to know regardless, that actually provides an explanation for a decision. So the way LIME works is you give the model your financial data, which is a point in Rn, so a point in Q. What LIME will do is it will build a linear model that approximates the complicated machine learning model around the point Q. Okay, so it's a local linear approximation of what the machine learning model does. And if you think about what this local approximation does, it basically shows you what are the weights that are given to different attributes of your financial data. And based on those attributes, it decides whether to accept or not. So attributes that have a high weight under this linear model mean that they had a lot of influence on the decision. Yeah, so by looking at the attributes that had high weights, you can get an explanation for why the decision was the way it was. Okay, so this is called LIME. It's actually kind of a complicated algorithm to produce these decisions. It has to kind of run the model on lots of points around Q, build a linear approximation, and that linear approximation is the explanation for why the model did what it did. Yeah, does that make sense? That once you have a linear approximation, the high weights of the linear approximation tell you which attributes were used to make the decision. So what we were wondering about is, well, you submit your data to the bank, a decision comes back, an explanation comes back, but you have no idea that they actually run the model correctly, that maybe they just made up the explanation, who knows what they actually did. So, well, so, we're cryptographers. So to us, every problem in the world can be solved using cryptography. So let's try to solve this problem with crypto. So what happens here, what would happen here is basically the bank would commit to their model. So you can see that Alice has a commitment to the model theta. And then what this X proof system does is it actually provides a proof to the user. And the proof basically proves that, first of all, the commitment is really a commitment to the parameters theta of the model. It shows that the decision really is the result of applying the model to the query that Alice sent. And the important part is that, in fact, the explanation that you received is, in fact, a Lime explanation for the query queue using the parameters theta. Does that make sense? So basically, the challenge for us was how do you implement this predicate? The first two steps were actually done before. This is the classic problem now has a name. It's called ZKML, ZK in machine learning, which is how do you prove that a committed model was evaluated correctly? That's the first two steps. What's new is basically proving that Lime actually was evaluated correctly too. So that actually took some work in basically implementing Lime efficiently in ZK. But we did that, and it works. And I guess I threw in a graph from the paper. We looked at 3 different models that are used in financial applications. Like this is an income predictor, a loan application risk predictor, and so on and so forth. And we extended this library called Ezekiel, EZKL, to actually build these proofs. So this is just an extension of a standard library to do ZKML, and you can see that like within a minute or so, we're able to produce these proofs. Again, there's probably a lot more work to do here. We can probably do this much faster. There's probably other models to experiment with, maybe use other libraries than EZKL. But generally, this question of like how much can we prove that ML models work correctly? Not just that they work correctly, they provide the right explanation, maybe that they're fair and so on, is all open area territory for building strong ZK models. Okay, so that was just kind of my general examples of things that we can do with SNARKs now that we couldn't do a decade ago, which is, again, thanks to this community, thanks to the fact that SNARKs have improved so much. So now I'm going to switch gears. So now for something completely different. So now I'm going to switch gears, and we're going to talk about LatticeFold. Yeah, so good. So the point of LatticeFold is basically to provide, to look at a post-quantum SNARK. And so let's see what can we say about post-quantum SNARKs. Okay, so let's get started. So far, so good? Okay, let's do it. All right, so really, if you zoom out, we sort of have 3 families of SNARKs. Yeah, so there's SNARKs based on pairings. Maybe I should have written curve-based SNARKs, but really the best ones are based on pairings. We have hash-based SNARKs, and we have lattice-based SNARKs. Yeah, these are kind of the 3 families of SNARKs. What's interesting, whoa, this is kind of dangerous. Okay, what's interesting is that if you look at the proof sizes that they generate, they're actually quite different. Yeah, so pairing-based SNARKs generate relatively short proofs. The hash-based and the lattice-based systems generate much larger proofs. Verification times are also quite different. You can see, well, what can I say? So somehow lattice-based SNARKs, at least some of the ones that came out recently, the verifier has to do relatively more work than in the other systems. And finally, I guess the thing that's of interest to us is this question of folding, which I'll say more about in just a minute. And so when you look at folding, again, we'll talk about folding in just a minute. Folding is a way to do recursive SNARKs. So if we want to prove a large statement, how do we break it down into small statements and do these proofs piece by piece? One at a time, piece by piece. Folding using pairings actually turns out to be quite fast and quite simple, as we'll see in just a minute. For hash-based SNARKs, this is harder. There's a system called ARC, a relatively recent system that shows how to do folding for hash-based SNARKs. It's a bit more complicated than for pairing-based SNARKs, but it can be done. And the question we wanted to explore is basically how do we do folding for lattice-based systems? So the question was, is it all possible? Is it efficient? Does it work well? And what I want to show you is that even though lattices have so far maybe have had some issues with building competitive SNARKs, lattices are great for folding. Yeah, so if there's one takeaway from this talk is that lattices are really, really good for folding, and that's kind of what I want to show you. All right, so let's get to it. All right, so I guess I have to start at the beginning. I didn't know exactly what level what level I should start. So let me start at the beginning and let's talk about IVC PCD. So I like to call these incremental verifiable computation or proof carrying data. I like to use the term piecemeal SNARKs for them. Really what we're doing is we're taking a very large statement that we want to prove, we break it up into small statements, and then we prove every small piece on its own. So I like to call these things piecemeal SNARKs. And the way this works is, you know, if you have 1,000 transactions that you want to verify, what you would do is basically, I guess we saw these pictures earlier today. What you would do is basically you would verify the proof incrementally. You would verify the first I transactions, then that proof for the first I transactions would go into the next verification circuit. You would build a proof that the next transaction is correct, and so on and so forth. Yeah. So basically, at every step, you build a proof that all previous steps were correct, or rather, that you have a proof for all previous steps along with the current transaction, and that gives you the proof for the next step. Okay, so this is kind of a standard IVC structure. I imagine everybody here is familiar with this, I hope. The problem with this is that this is a little problematic. Yeah, so on the plus side, this greatly reduces the memory footprint of the prover, because the prover is only proving relatively small statements. The other huge benefit, the reason people like to use recursion, is you can start to build the proof before the statement is fully known. If you have 1,000 transactions, you don't have to wait for all 1,000 transactions to be given to you. You can start to build the proof as the transactions come in. With a monolithic SNARK, where you prove the entire statement at once, you would have to wait for all 1,000 transactions to come in, and only then you can start building the proof. And also, it turns out this is highly parallelizable. Here I explain it using a line, but of course you can do this also using a tree, in which case you get nice parallelism. The problem with this approach, though, is it's kind of complicated. Yeah, so first of all, this verification circuit is not simple, and so now we have to absorb the verification circuit into our SNARK verifier, into the circuit we're actually proving. And the other problem is the prover has to generate a full proof at every step of the computation. Okay, so there's kind of two limitations. Yeah, complicated verification and full proving at every step of the computation. So the question is, can we do something better? And that's exactly where folding comes in. Okay, so that's a beautiful idea of folding, which turns out we can simplify both of these steps while retaining all the benefits. So let's see. So let's start with folding schemes. So to introduce folding schemes, I have to tell you about linear homomorphic commitments. I think everybody here knows what a linear homomorphic commitment is. I'll just say, given a vector, we commit to this vector, and the homomorphism basically says that given two commitments to two vectors, it's quite easy to build a commitment to their sum. Okay, so those are linearly homomorphic commitments. It turns out, again, this ARC system that I mentioned before actually is able to do folding without linearly homomorphic commitments, but we're not going to talk about that here. Here we're going to focus on proof systems that use linear homomorphisms. Okay, so what do we do? So in folding, the first thing we have to do is we have to rewrite our statement in a way that's amenable to folding. Okay, so we're going to call this, so we're going to take our NP statement, which we call R sub NP, and we're going to rewrite it in terms of R sub com. Okay, so what is the difference? The difference is relatively simple. All we did here is we basically exposed a commitment to the witness in the statement. So you notice we expand the statement from X to X comma commitment to witness. Okay, so that's the new statement U, and the witness still stays the same. And what we're proving is that X and W are in the language, are in the relation, and that in fact CW is a commitment to W. Okay, so that's kind of the first step that we have to do in preparation for a folding scheme. Great. So the way the folding schemes work themselves, the way they work now with this R sub com, again, I think we saw this picture earlier today, but I'll go through it again just to make sure everybody remembers it. So the way folding works is basically we start with two statement witness pairs, U1 W1 and U2 W2. The folding prover will work very quickly to produce a folded statement, so U tilde and W tilde, plus a folding proof that just the folding was done correctly. Okay, so this is this little proof pi that's produced. What the verifier will do is it will take the two folded statements, it will take, the original statements U1 and U2, along with the folded statement U tilde, and the folding proof pi, and decide whether this is a correct folding or not. Okay, so that's basically what folding, syntactically, this is what folding does. Of course, it has to be complete. So if the prover and verifier are honest, the verifier should accept. That's the security property. By the way, the best way to explain the security property is through this concept. It's a new concept called a reduction of knowledge. It turns out it's a very elegant way to express what folding does. So please use this terminology of reductions of knowledge. What it does is it shows, so folding basically shows that it reduces knowledge of W1 and W2 to knowledge of W tilde. So if you know a witness for U tilde, that should imply that you know witnesses for U1 and U2. So yeah, again, we're reducing knowledge of witnesses for U1 and U2. Sorry, we're reducing knowledge of U tilde to knowledge of witnesses for U1 and U2. Yeah, so I just wrote that informally over here, that if the verifier accepts what the prover produced, the prover then must know original witnesses for the original statements. By the way, I should say reductions of knowledge is a generalization of knowledge soundness, and knowledge soundness is a reduction of knowledge to the true statement. Yeah, but more generally, you don't have to reduce to the true statement. You can reduce to more complicated statements. Okay, so we understand folding in terms of reductions of knowledge. Okay, so that's the formal property. I hope everybody okay with this? That if you know a witness for the folded statement, you must know witnesses for the original statements. That's what folding does. And then once we have a folding scheme, oh yeah, now I should say the whole point of folding, what is the point of this exercise? The whole point of folding is that actually the prover now doesn't have to produce a full proof. The prover is just producing a folding proof, which is much, much faster. The verifier doesn't have to verify an entire SNARK proof. It just has to verify a folding proof, and both of those things are dramatically easier than producing a proof and verifying a complete proof. Okay, so that's the reason why we like folding so much over recursion. Yeah, there's some caveats. Folding doesn't apply everywhere. There's some caveats which we'll get to later. But generally, folding is, at least if you're producing a single proof by a single prover, folding is a better way to do recursion than full recursion. Okay, good. So yeah, so I guess this part I can skip over quickly. So once we have a folding scheme, we can build a full SNARK from it, just like we did before. This part I think I'll just skip. Okay, so how do we build these folding proofs? All right, so how do we actually fold? Well, it turns out we need a linearly homomorphic commitment. So which linearly homomorphic commitment are we going to use? The first thing that comes to mind, of course, is Pedersen commitments. Yeah, so here we wrote down what a Pedersen commitment is. So the nice thing about using Pedersen commitments for folding is the folding proof is the proof that the folding is correct is relatively, it's not too complicated. It basically follows directly from, it's a 3 special soundness proof, and we get a very nice construction, very elegant folding scheme out of it. This is how Nova, Hypernova, and all these related folding schemes work. The problem with using Pedersen commitments in this context, though, are substantial, right? So first of all, when you use Pedersen commitments, you have to use relatively large fields. You have to use a 256-bit field, or maybe even more, so large fields. The other issue is that the folding verifier, it turns out, has to do both field operations and group operations. Since SNARK circuits only support one field, yeah, either FP or FQ, whichever one you choose, you're gonna have to do some field emulation inside of your circuit. So that basically means that the folding verifier is not as efficient as it could be because, again, it's doing some non-native arithmetic as part of verification. That's the issue with Pedersen commitments, and of course, it's not post-quantum secure, which means that the system is not going to be binding as a result. Okay, so what do we do? What can we do instead? So the natural question to ask is, can we fold using a lattice homomorphic commitment? Yeah, and the whole point of what I want to show you is, yes, in fact, we can. This system is called LatticeFold and its derivatives, but unfortunately, as with everything with lattices, there's lots of complications. Yeah, somehow with discrete log systems, everything just works as intended, and with lattices, you always have to work harder to get things to work. So that's what I want to walk through. So the benefits are now all of a sudden you're using much smaller fields, only 64-bit fields. And actually later today there's a beautiful talk by Nethermind. I highly recommend everybody go to this talk that actually experiments with LatticeFold and its derivative. One of the things they show is that for reasonable numbers, Ajtai hash is about 30 times faster than the Pedersen hash, which suggests actually that the folding prover and folding verifier could be dramatically faster than if we use Pedersen. Unfortunately, it's not quite as good, right? So 30x speed up would be fantastic, but as I said, with the minute you start doing Ajtai hashes, things get complicated, and the extra complications eat up into this 30x potential. Yeah, so the dream is that we actually would get a 30x speed up in the folding prover. The reality is we're not quite there because of all the extra complications that come from lattices. The other nice thing about lattices is that you're only using one field. It's not like you have two fields as we did with Pedersen. Here, when whatever vector you're hashing, the hashed vector happens to be in exactly the same field. So as a result, you don't have to do any field emulation. And as far as we know, at least we believe, this is post-quantum secure. OK, good. So that's the goal. So now the question is how to do it. So the first thing I have to do is remind you a little bit about how, again, I just wanted to make sure everybody's familiar. I didn't want to assume everybody knows lattices. So let me just remind you how Ajtai hashes work. So we fix our prime. We fix a bound size, which in this case is 2 to the 16, and we have some dimension n for the vectors we're going to compress. So given a vector w, in this case its L infinity norm is bounded by beta. The way we hash it is like as simple as you can imagine. We just do a matrix vector product, A times W, and that's it. And you already see that W itself lives in the field FQ. The hash of W also lives in the field FQ, or ZQ rather, so we end up with only one field that needs to be supported by the circuit. So that's issue number one. The problem is this hashing, this matrix vector product is not by itself collision resistant. Of course, a matrix vector product cannot be collision resistant. It's only collision resistant when the input vector is bounded in norm. Yeah, and that's what causes all the problems, as we'll see in just a minute. Okay, good. Yeah, of course, it's linearly homomorphic, so that's trivially linearly homomorphic, so there's nothing more to say there. But it is important to remember that it's only binding when we apply it to lower norm vectors. Now, some people were asking me, or rather complaining about LatticeFold, saying, "Oh my God, you have to store this big matrix A in order to do all your operations." Well, it turns out that's not really true. You don't have to actually store the matrix A, just like we do in post-quantum crypto. The matrix A is often generated from a seed. What's interesting is we don't even have to use a very complicated generator. So this generator would have to run inside of your SNARK circuit. So we want to use the simplest possible generator we can use. And in fact, that is the case. We can use relatively simple generators to produce a and actually, that's a good question. Like, what is the most SNARK-friendly generator to generate the matrix A that would retain the security of the Ajtai hash? But that's another issue that needs to be studied. Okay, and finally, so finally, this is only describing the Ajtai hash over ZQ. Unfortunately, that requires, as you can see here, a matrix vector product requires basically lambda times n operations, and the question is, can we make that better? So how do we make that better? How do we speed up the Ajtai hash? Somebody want to yell it out loud? How would we speed up an Ajtai hash? Somebody has to know the answer. So what I described here is over ZQ. If you don't like ZQ, what do? Yeah, you go move to rings. Exactly, rings. Rings are our friends, right? So, so instead of working over ZQ, instead we're going to use an RQ. Yeah, that's what people were saying. So we move to a ring, and I just want to stress, like, why is it so useful to move to a ring? When we move to a ring, what happens is instead of doing a matrix vector product with the vector and the matrix over ZQ, instead what we're going to do is we're going to do a matrix vector product, except now the vector and the matrix are all elements in our ring. Since the ring has every element in the ring is represented by D elements, what we can now do is we can shrink our vector and we can shrink our matrix by a factor of D. Right, so the matrix shrinks both in a vertical and horizontal direction by a factor of D. Our vector shrinks by a factor of D. The commitment shrinks by a factor of D, and everything shrinks. Okay, so that's great. Naively, you would say, "Oh, that doesn't really help much." Sorry. Again, I have to state this again and again. It's very important that this operation is only binding when we're applying it to lower norm vectors. Okay, the problem, of course, the benefit of this, of course, is that now it turns out the complexity is only, well, let's see. So we can just calculate the size of the vector is, the matrix vector product is now going to be lambda times n divided by d squared, right? Because everything, I guess, what is it? The horizontal direction shrunk by a factor of d, vertical direction shrunk by a factor of d. So the number of operations is lambda n over d squared. But of course, each operation now is more complicated because we're multiplying two ring elements. If we do that using FFT, that takes roughly d log d times. So overall, we just improve things by a factor of d. Okay, so this is why whenever we use the Ajtai hash, we're always using rings instead of ZQ. Okay. All right, so far so good. All right, so the question then is, how do we fold with the Ajtai hash? So let's get into how actually folding works. So when you do folding, you kind of do the oldest trick in the book. Yeah, the way we fold is actually by taking random linear combinations of the input statements. So remember, we have our commitments to the witness and we have our witness. The way we fold is we take this random linear combination. So here you can see the folded commitment, the folded witness, are these random linear combinations, and immediately you run into a problem. What is the problem we run into? Remember that the commitment has to be an Ajtai hash of W tilde. So C tilde is an Ajtai hash of W tilde. The problem is, once you start taking linear combinations, random linear combinations, this W tilde is no longer short. Yes? So boom, we ran into a problem. So this basic folding method just doesn't work. So what do we do instead? So this is basically what this says. If we just did regular folding by taking linear combinations, that would no longer be sound. So what do we do instead? So so we solve it in the usual way that we solve problems with these norm bounds. We are going to do some decompositions. So the way this will work is, let's see. So we take our original vector. So we take our original statements. What we'll do is we'll break them up into, we'll do decomposition. Yeah? So suppose we have an element A that's low norm. We'll split the element A, or rather we'll write it base B. So we'll split it up into its digits. And then we'll apply the Ajtai hash basically to this reduced norm vector. So really, the way this works is the following. So we have our two statements that we're trying to fold. What we'll do is we'll take each one of these statements, we'll split it up into, let's say, 2 or more statements. Here in this case, it's only 2 statements. So instead of folding 2 statements, now we end up with a problem where we need to fold 4 statements. We fold these 4 statements together, and because the norms were reduced, even though we sample our linear combinations in what's called a sampling set, we end up with sufficiently low norm vectors. Okay, so random linear combinations work if we do the decomposition ahead of time. Okay, so that was easy, not very interesting. Everybody's kind of familiar with this approach. The bigger problem is the next challenge. So this basically ensures that W hat is in the right interval so that the Ajtai hash is committing. So far, so good. Yeah, so we got over our norm growth problem. The bigger problem is we have to build an extractor, right? So the way reductions of knowledge work is, well, you have to show that you can extract witnesses for the original statements from a witness for the folded statement. Of course, the problem is when you try to do that, the adversary could give you an arbitrary malicious witness. And the problem with this, as usual, is when you try to extract twice, what will happen is you'll end up multiplying. So here, we rewind, we get our 2 witnesses that we're trying to, from which we're trying to extract. And the way we extract is we have to multiply by this gamma 1 minus gamma 2 inverse. Gamma, remember, is the random linear combination. So now we have to multiply by gamma 1 minus gamma 2 inverse. That is, again, a high norm value. So the result is we are extracting a high norm witness, which is invalid. We're not allowed to extract a high norm witness. We have to extract a low norm witness. And this is a bigger problem. Yeah, so how do we force the extractor to extract actually a low norm witness? So the only way we know how to, so maybe it would be great if there were other ways, if anybody has other ideas for how to force the extractor to extract a short norm witness. The only way we know how to do it is by actually requiring the folding prover. Yeah, it's by requiring the folding prover to prove to prove that the original witnesses W1 and W2 are themselves low norm. Okay, so if the original prover proves that the original witnesses were low norm, that would say that basically that we can use that to enforce that, to ensure that the extractor will actually output low norm witnesses as well. Okay, so all of a sudden we're trying to do folding. We use decomposition to avoid norm growth, like trivial norm growth of the witnesses, but all of a sudden now we have to include a range proof to make sure that the extractor actually works correctly. So that's kind of painful. That's kind of the unfortunate part of this, and that really eats up into the 30x potential speed up that we get from using the Ajtai hash instead of the Pedersen hash. All right, so what do we do? How do we do this? So in the original LatticeFold, what we did is that we used kind of a range proof. Oh, by the way, I forget, maybe I need to make it clear. What do I mean by a range proof here? So what we have to do basically is to prove, I should probably point that out more explicitly. What we have to prove is actually that the vectors, that the elements W1 and W2, which are now vectors over our ring, basically every element in that vector, all of its coefficients are small. So the norm bound applies here to the coefficients of the vectors, the coefficients of elements that make up the ring elements. Okay, I think we saw something like this in the previous talk. So this problem actually comes up here again. So in the original LatticeFold, what we did is we basically used a bit decomposition method to do the range proof. The bit decomposition method was particularly useful because it allows us to use a sum check to do the range proof. The sum check combined nicely with the statement that we're trying to prove. The statement was using this customizable constraint system, CCS systems. So we could encode the statement and the range proof in one sum check and get all that done at once. Yeah. So that actually introduced quite a bit of overhead. And in fact, the talk later today that Nethermind is going to give, I'm not going to steal their thunder, just come to that talk and you'll see how this compares to Pedersen-based folding schemes. Yeah. So they have a full implementation of this method. I think it's fascinating to see how it compares to Pedersen folding schemes. I'm not going to tell you. You have to go to that talk to see if it's faster or slower. Okay. What I will tell you is we can do better now. So LatticeFold Plus is a much more efficient range proof, uses a much more efficient range proof for W1 and W2. It turns out for convenience reasons, we also changed a little bit how LatticeFold works. So what we do, the way I described it so far is we decompose and then we fold so that the folded statement has a short norm. Rather, the folded witness has a short norm. And it turns out in LatticeFold Plus, it turns out to be, it's better to fold and then decompose to reduce the norm of the folded statement. So I thought I would just end by showing you a little bit of how the LatticeFold Plus range proof works. Actually, how am I doing on time? Oh, wow, fantastic. So I was going to go through this very quickly. Okay, so the way this range proof works is basically as follows. Suppose we start off with a simpler problem where we just have n scalars, and we want to prove that these n scalars are in a certain interval. Okay, so they have low L infinity norm. It turns out what we do is this is kind of a cute trick. So what we do is we take this vector and then we commit to elements where we encode this vector as monomials. Yeah, so these are elements in RQ. So each monomial is an element in RQ, but it's kind of odd that literally the FIs become exponents. This actually makes sense because these are numbers between minus d over 2 and d over 2, so we can encode them in our ring. So we end up with a vector of n monomials. Now what we have to do, the prover now, is to prove two things. First of all, he has to prove that f is really constructed correctly. So f is really a set of monomials that represents f1 to fn. And second of all, we have to prove that all the exponents really are in that interval. And it's kind of a magic that this works, but the cool part of the paper is that basically these two proofs, the fact that f is constructed correctly and that the monomials, their exponents, are in the right interval, actually that can be done using a purely algebraic check that's actually really quite fast, and it's just a simple sum check. Yeah, so I would say this is the heart of the paper. I mean, if I was giving a technical talk on LatticeFold Plus, I would spend all my time on just explaining exactly how this works. But yeah, this was supposed to be a higher level talk. So I'm going to leave it to you to maybe look at the paper and see how this works in detail. Yeah, the point is there's no more bit decompositions, so everything is purely algebraic and just using simple sum checks. So this should be quite a bit faster than the basic LatticeFold method. We expect about a factor of 5 speed up over basic LatticeFold. Again, if you come to the Nethermind talk, they will tell you exactly what the running times look like. So please go to that talk. All right, so, okay, so there's one more complication. I'm out of time. Am I out of time? Okay. You know what? I think maybe I'll skip this. It turns out if you want to shrink the proof, there's this extra trick called double commitments, where we commit to a vector of commitments, something along the lines of what was used in Labrador. But I think maybe I'll skip the double commitment method. This turned out to be kind of a fairly technical part that maybe I'll skip here. Okay, so to summarize, basically we have these new LatticeFold, we have these new lattice-based folding schemes. There's the original LatticeFold, there's the improvement LatticeFold Plus, there's a third improvement called Neo that gives an orthogonal improvement to LatticeFold. So we kind of have two improvements now to LatticeFold, which is very exciting. The point is we can now do folding in a small field. We have very efficient verification circuits. It's post-quantum secure. It supports these high-degree constraint systems. No setup. And so, yeah, so my point is that if you want post-quantum piecemeal SNARKs, it looks like lattice-based folding is kind of a good way to go. And the interesting thing is, I think this is kind of one of the first times where a post-quantum SNARK system might actually be better than a pre-quantum SNARK system. So that's kind of exciting because we haven't had that before. So yeah, so I think I'll thank you very much. I'm a little bit jet lagged, so hopefully this was clear. But thank you very much, and I'm happy to take any questions.
Thank you. Thank you, Dan. We're just happy that you didn't fall.
Yes,
so
that's right.
It's all good. Any questions?
Thank you for the great talk. I was wondering, is there any bound on number of times we can fold?
Yeah. So it's a great question. So there's no a priori bound on the number of times we can fold. That is, we don't know of any attacks. The proofs, of course, kind of prove only one folding step. And then it's up to you to decide how many times you want to trust the system to fold. Yeah. But that's kind of a generic issue with recursion and folding in general. Yeah. It's a very good question. Even more than constant. Yeah, you can do. Yes. That's right. This would inherit exactly the same results. Exactly. Yeah. Yeah, but constant is not that interesting. So it wouldn't be an interesting recursive method if all we could do is constants. Yeah.
So you're saying that all folding schemes today are lacking some form of concrete security when it comes to the implementation?
And let's just say, maybe I'll say in more way than one, but maybe we'll just leave it at that. There's a lot of work to formalize the
concrete security.
There's sort of inherent limitations in our ability to prove these recursive methods, having to do with the random oracle model. In fact, Ron's talk from yesterday kind of shows that maybe these are not just limitations. Maybe there's more than limitations here. Yeah. And so that's the world we live in.
Thank you. More questions? All right.
Amazing work. I wanted to ask you mentioned at some point in the extraction that you're using rewinding, and I want to ask about the compatibility with post-quantum, or is it post-quantum in the sense that we don't know, that it's classically secure and we don't know an attack?
Yeah. Oh, it's the latter. So it's exactly it. So yeah, look, there's a lot more work to do here. Absolutely. So let's see. So what you're asking is if we're trying to let's see, if we're applying rewinding, how does rewinding play with the post-quantum world? And of course, how does rewinding play with a quantum random oracle model? That's the issue. How does it work with a quantum random oracle model? Yeah. So there's more work to do here. So for sure, that would need to be analyzed as well. So it's a very good question. Yes.
You actually get
Yes.
The idea is to try and get the proof into a margin.
Yes, actually, I just talked to Kevin. Actually, they're like his goal in life is exactly to build a lean proof for Fermat's last theorem. Yeah. That would be amazing if he can do that. They're not quite there. That's probably years away. Yeah. But yeah, then you could build a SNARK out of it, and you can print on your T-shirts a proof of Fermat's last theorem. Yeah, absolutely.
All right. Let's thank the speaker again.
Thank you
so much, Dan. Thank you all for your patience. I know we're all hungry. Let's go for lunch, and we'll be back at 2:50.